Okay. The quiz for today is beam observed be at angle 2430 degrees and t equals 30 seconds. And 2520 degrees and t equals 33 seconds. We assume the angle is uncertain by plus or minus 15 degrees. And the times are each time is uncertain by plus or minus 0.2 seconds. What's the average rate of change of angular position with respect to time? Now, these are your angular positions, and here are your times. Okay? And you ought to know what an average rate of change is if you've had pre-calculus and calculus. Okay? And then, what is percent uncertainty in the average rate according to this information? Now, people took the quiz and people were, yeah, here's my observation, pretty good with percent uncertainty of the individual quantities, although I saw errors on that. But not real good about what to do to find the uncertainty of the calculated average rate. So I've asked everybody as an assignment to go back and read their chapter a little more carefully, if necessary, and be very specific about what rule you're applying when, and rework this problem and try to get it 100% and bring that to lab on Friday. Lab is from 11 to 2. By something that was more or less the class consensus, that was close between 10 and 11, but given the reasons people gave and so forth, the tiebreaker was we go with 11. Okay, now according to what people self-reported, people understand vectors pretty well. So we kind of concentrated today on a couple of aspects of vectors, and we'll deal with more aspects on Friday in connection with the rotating beam experiment and other things that we can do. Okay, so I said, okay, we've got vector A, 2i minus 3j, vector B, 4i plus 6j. Everybody knows how to add these vectors. I assume everybody knows how to subtract them. Everybody knows how to do a parallelogram to sketch the resultant of two vectors. Question is, what angle does this vector make with the positive x-axis as measured counterclockwise, which is the way vectors are measured, especially if we're doing analytical trigonometry. So I drew this picture. I mean, here's 2 units, here's -3 units. So this is a picture of a vector 2i minus 3j. We haven't drawn the vector B, but there it is. What's the angle between 0 and 2 pi of this vector? Well, I got an answer like 56 point so many degrees, but people didn't say, the person didn't say degrees, said 56.4, whatever it was. Well, then that answer was 66.4 radians, because if you don't specify the measure of the angle, you are talking about radians. That's the default measure of angle in mathematics, okay, and in physics. Now in engineering, I see it all the time. Engineers will write down angles in degrees without any indication that it's in degrees. Engineers get in a hurry. I'm not going to question what engineers do. As long as they understand what they're doing, fine. But when you're in physics class, you're going to communicate it correctly. Just because it's a good habit, you can vary your habit depending on your context. Okay, whatever's more appropriate. Whatever communicates what needs to be communicated. Okay, so how do we find this angle? Well, I didn't ask for an approximate angle. I didn't ask for an angle with decimals. I asked for the angle, which means I was asking for an exact result. And 56.4 degrees, it's correct, is in the right ballpark at least. It might be a good approximation, but it's not exact, because I don't think you can do this angle inexact. Actually, you kind of can, because you can combine some rules for double sums of angles and differences of angles, and do all kinds of fun stuff. And maybe you get an exact representation of this angle. I haven't even asked the question. Okay. Now, find the angle. Well, let's just read the definition. First of all, the angle is measured from here to here. This is a positive direction for rotation. That's the positive direction for measuring an angle with reference to a pole or the x-axis, positive x-axis. The reference angle is the angle that the vector makes with the closest part of the line of the pole. Okay, well, I'm not going to even elaborate on what that means, but I think that's probably correct. But this is the angle that I'll call theta ref. And for this angle, you could draw this blue triangle, opposite side 3, adjacent side 2, and figure out what the reference angle is. Well, the tangent is obviously the opposite over the adjacent side. That's 3/2. Now, the size of the rectangle, you might want to say, well, the opposite side is -3. No, legs of the triangle, the sides of the triangle have measured distance, or measured by distances, not directed distances. They don't have negative values. Okay, that triangle has 3 units here, 2 units here. In the plane, yeah, the 3 units go in the negative y direction. That's going to be important by the quadrant of the angle and so forth. But right now, the reference angle has opposite side 3, adjacent side 2. And the tangent of that angle, therefore, is 3/2, so that the angle is the arctangent. Theta ref would be the arctangent through. Okay. Now, if we do it analytically, the tangent of theta now, theta being this angle, is y/x, the y coordinate here divided by the x coordinate, which is -3/2. And theta is the arctangent of -3/2. Ultimately, we wanted an angle between 0 and 2 pi, so we just add 2 pi, the angle of the complete circle, to the arctangent of -3/2, which is a negative angle. It's going to give us an angle between 0 and 2 pi. I will comment that the vector 2i plus 3j, or sorry, -2i plus 3j is opposite this one. It also has a reference angle that's equal to this one. And if you do theta equals arctangent -3/2, you're going to get this angle down here, because the arctangent only gives you an angle between -pi/2 and pi/2. And you're going to have to know that when the x coordinate is negative, you're going to have to add pi radians, 480 degrees, whatever the arctangent you calculate here tells you. So this thing would be 180 degrees less than this, which is obvious. And you have to be able to deal with that. Both of them had a good trigonometry course, to the extent where if you didn't understand that, you do now. Okay, now we have the dot product. Now the dot product, and everybody claimed to be familiar with the dot product. I think they were. Dot product is easily calculated for 2 vectors. You multiply their I components, you multiply their j components, and you add them. So I components of 2 and 4, you got 2 times 4. J components of -3 and 6, you got -3 times 6. That's 8, and -18, which gives you -10. And that's the dot product of these 2 vectors. And the definition of the dot product, well, here's your definition. It's the magnitude of A times the magnitude of B times the cosine of theta. This is just a way of calculating it. And the connection between this and this is just a matter of using the law of cosines at a high school trigonometry level. And it's not difficult. If you're interested, you can look that out and look it up. In any case, there we have it. And then I asked, okay, can you use this to find the angle between the vectors A and B? How could you use it? Well, people didn't have a real good answer to that. But the answer is actually very simple. You take this definition and theta's in there, that's the angle. If you know the two vectors, then you can calculate the magnitudes and you calculate the dot product, you figure out the angle. In other words, solve this equation for theta. Now you solve it by cosine theta, you divide both sides by the product of these magnitudes, and you get this expression. That's cosine of theta. To get theta, you take the inverse cosine of that. And there it is. That's an easy way to find the angle between two vectors. And you're not confined to 2 dimensions. It works just fine in 3 dimensions. And vectors extend into higher dimensions. Everybody in the class has an linear algebra. You understand a vector could be expressed in any number of dimensions. Okay? You'd have a vector of 4 dimensions. That's gives it nothing. It's hard to do. You can't really visualize it. You'd have a vector in 3 million dimensions, and they do arise in data analysis, believe me. Okay, actually, I'm not an authority on data analysis, but to say, I'm sure you can believe that. I'm sure that's true. Okay, although not from my direct experience. I haven't done data analysis, but I have 3 million dimensions. Okay. Now, there's another way of expressing the vector A. In this case, it'd be the square root of 13 times I cosine theta plus I sine theta plus, oh boy, I had I on both of those. Got to keep my eye on myself. They referred to that a couple of times. Never noticed I've written I. And that should have been J. Just make sure you got that right. That's something you should be familiar with. This is a unit vector in the direction angle theta. Theta is the arctangent, -3/2. And if you plug the arctangent of -3/2 in here, whether or not you add 2 pi to it, you're going to get this. Now, if you do a decimal approximation of the arctangent of -3/2, you're not going to get exactly this. You're going to get either a 1 followed by a bunch of 9s, depending how accurate the approximation is, or 2 divided by a bunch of zeros and 1 and all that stuff. But there you have it. Okay. Assuming the theta is the arctangent -3/2, then this does come out if you calculate it to be this. Okay. So that's a quick synopsis of what we're going over related to the dot product. It's a handy way of finding the angle between 2 vectors. It has a lot of other applications. You've seen a lot of them, I think, in linear algebra. You're going to see a lot more next semester in multivariable calculus if that's in your future, which it is for most of the classes. Okay. Now, we're going to do cross product. Okay. Now I'm going to do cross product, basic definitions. Okay. And this I can define it like this. Okay. That's one way of defining it. Now the way it's really defined is this vector cross product of A and B would be a vector perpendicular to both A and B. Its magnitude is equal to the magnitude of A times the magnitude of B times the sine of the angle between. So it's kind of a lot like this, but of course what you get is a vector, not a scalar in this case, not just a number. I'm going to introduce it this way because it turns out to be the same thing. If A equals A1I plus A2J plus A3K, and B equals B1I plus B2J plus B3K. Notice both of these are vectors in 3 dimensions. Cross product is only defined in 3 dimensions. It's not defined in 2. It's not defined in 4. It's not defined in any other number of dimensions. Okay, so if you have these 2 vectors, then how do we calculate the cross product? Well, I do it over here. I think I got it wrong. I'll try to correct it as I go through it. I think I got a sign on that. I cross J, the I vector cross the J vector is equal to the K vector. Now, what I mean by the I vector cross the J vector? Well, the I vector is in this direction, the J vector is in this direction. So we use the right-hand rule. Put our fingers in the direction of the I vector and orient our palm, not up, not back this way, not upside down, but this way, so that when I curl my fingers, they go into the direction of the J vector. So here they're in the direction of the I vector, they're curled to the direction of the J vector. The thumb, excuse me, has no choice but to be pointing upward, and that's the direction of the cross product, which is in the direction of the K vector. And cross product is equal to the K vector. I could say more about that. Product of the magnitudes, these both have magnitude 1, so the magnitude has to be 1. Because the angle between them is 90 degrees, the sine of 90 degrees is 1, etc. They have to equal K. There you can see it geometrically, and if you want to get really used to the right angle. So I cross J is equal to K vector. And then you can work it out, the I cross K. Okay, here, fingers again in the direction of I. Where does my palm go? It goes so that my fingers will curl toward K. And that gives me the direction of the negative J vector. There it is. J cross K is I. Okay, J's here. K is up here, so I better turn my hand this way so that I can turn J toward K. And there's my thumb pointing in the positive X direction, the direction of the I vector. Then if I reverse things, J cross I, okay, well, here's J again. Let's say J cross J with I, I've got to turn my hand like this so that my fingers cross toward I and I get negative K. Well, it turns out that the multiplication is anti-commutative. You can work it out with your right hand. K cross I is going to be J, which is opposite to negative J. K cross J is negative I, which is opposite to I. Also, I cross I, J cross J, K cross K are all 0. The definition involves a sine of theta, and each vector makes angle 0 with itself, and the sine of 0 is 0, so the cross product is 0. You can fill in the details. Okay, now if I want to do A cross B, and I want to modify the thing I did in a good way, making corrections up there. There we go. Okay. Now, A cross B, of course, is just A1I plus A2J plus A3K cross with B1I plus B2J plus B3K. It's my orange chalk. Where does this come from? So thing, okay. Triangular shaped piece of building out of that. Oh, here it is. Okay. Now, I do A cross B, I can write it like this. There's your A vector cross your B vector. Distributive law applies, meaning that A1I multiplies B1I multiplies B2J multiplies B3K. Okay. And then A2J multiplies each of these, B3K multiplies each of these, and there are 9 possible products. We can kind of group them as you'll see. Okay, first, A1I cross B1I is A1B1 times I cross I. Well, I cross I is 0, so we don't do that. And we're not going to do A2J times B2J. We're not going to do A3K times B3K. We understand that those are zero. If you really want to write them out, that's fine. It's maybe not a bad idea, but for brevity, I said this one's zero, and I didn't bother writing the other J cross J and Q cross K. Because what's really interesting is the I cross J and all that stuff. Okay, so we do A1I cross B2J. Well, that's A1, A2, I cross J. Right there, A1, B2, I'm sorry, A1, B2. Well, there's A1, B2 times I cross J. Now, said we're going to group things. There's another way to do cross product involving I and J. And that's the A2J and the B1I. So okay, where to go? Fell on the floor and I disappeared. Okay. It didn't break. Okay, now the A1 I times B2J is represented here by this as part of this problem. Okay, the A2J times B1I. Well, it's going to be A1 B1 times J cross I. Of course, J cross I is the opposite of I cross J. So just put the negative sign on A2 B1 and multiply by I cross J. All right, so there it is. And right there is our I cross J. Now, I went ahead. I'll go ahead right now. What's I cross J? It's K. So that means we've got A1 B2 minus A2 B1 times K. All right. So we've got that. Now, let's do A2J. Now we've already done that by B1I, and we don't do J cross J. Zero, we do it, but it's zero. And A2J cross B3K. So that's A2 B3 times J cross K. And I messed it up down here. So we're at okay. On the K cross J, we've got an A3K cross B2J, which is A3 B2 times K cross J. Well, that's right. That's A3 B2 times K cross J. That actually be right. And then we have another cross product involving K and J, which would be A2J times B3K. So that's A2 B3 times J cross K, but J cross K is a negative, K cross J is to get a negative. Okay. Now, for some unfathomable reason, what did I do? Oh yeah, I was doing I cross K. We do the A1I cross B3K. That's going to be A1 B3 times I cross K. And then, of course, we'll have B1I cross A3K. So we have A3 B1 I cross K. So that's all correct. Okay, then I cross K is what? I cross K is negative J. So we replace the I cross K with a negative J. So we have the A1 B3 minus A3 B1 times J, but with a negative. Then I cross K. Okay, that's right, I cross K. Wait a minute. No, K cross J. K cross J is negative I. So we have a negative I on this. And I think this goes with that and that goes with this. Anyhow, write it out carefully and you should get it right. Now, I show you this simply because a lot of times, if a couple of these, if one component of this vector and one component of this vector is zero, it's actually easier and quicker to use the distributive law. So it can be useful to understand how the distributive law gives you this. It's also theoretically important. Since most of you have a polynomial calculus in your future, it's worth seeing. Okay. So I'm going to put a big question mark around these. I don't want to sort them out any further. What's wrong here is that only one of these should be negative. And I've never sorted out while I explained it. But one blind looking at it, and you might too. Okay. It's worth writing it out precisely. It's good practice. And again, it can be useful to understand how the calculations are. Okay, now, the way you're probably going to do it, this is not a definition, but it's a way of calculating it. A cross B would just be IJK with A1, A2, A3, B1, B2, B3. I think everybody recognizes this. I've expanded this by minors because a lot of times, the first time you learn it is not in linear algebra, and everybody's had linear algebra. So, linear algebra, just expand by minors. I just look at I, and then I do the determinant of this, which is A2B3 minus A3B2. So it's I times A2B3 minus A3B2. And then it's minus J times the determinant that I get. For the minor that I get when I eliminate the row and the column of J, which is A1, A3, B1, B3, there it is. And that's A1, B3 minus A3, B1. And for K, it's similar, plus K times the determinant of the minor I get when I eliminate the row and column of K, A1, A2, B1, B2, A1, B2 minus A2, B1. So it's easy enough to calculate. The actual definition of the cross product is the magnitude of A times the magnitude of B times sine theta. And the direction is what you get with the right-hand rule when you cross A with B. It's going to be perpendicular to both the A and the B vector. I did an example here, parallelogram. Parallelograms have a lot to do with vectors. You want to be able to visualize parallelograms, to do projections and cross products and all kinds of other stuff. And you do a lot of that in polynomial calculus, applied to the calculus. It gets really interesting. Anyhow, you got the A and the B vector. You're drawing a parallelogram. I incidentally say that the vector A plus B is just the initial point, common initial point of the two vectors up to the opposite of that parallelogram. But the other thing I can say is that the altitude of this parallelogram, it's kind of a dotted line here, kind of goes through the theta, but the altitude is the magnitude of A times the sine of theta. Because right there's a triangle, it's a right triangle with angle theta here, and the vector A on the hypotenuse. Well, the altitude is then clearly the length of that hypotenuse times the sine of theta, opposite side. Angle, and I think everybody's well aware of that. So that this calculation, the magnitude of B is the length of this base. Magnitude of A times sine theta is the altitude. Okay, magnitude of B is the length of the base. Magnitude of A sine theta is the altitude. That's pretty neat, and make sure you really understand that because it often helps. Then I do kind of a triple product. That's a little hard to see. I've got a vector A here. I'm sorry, vector A is here. Let's do the vectors A here and see. So here's the vector A. Here's a vector B. And here's a vector C. Now I say that A cross B, and here's A cross B. Some vector depending on the scale of everything, is perpendicular to both A and B. A and B, I presume, are in the XY plane, just to make it simple. C, they don't really look like they are, but they are supposed to be. When I first draw them, I had a couple of projection lines. They're kind of obscured by my shading of this three-dimensional figure. Then you have some vector C out of the plane. Well, first of all, the length of this vector represents the area of the parallelogram down in the plane. Okay. Now, if I dot C with A cross B, the vector will have a magnitude equal to the magnitude of A cross B times the magnitude of C cosine theta, where theta is this angle here. Well, C cosine theta, you've got a right triangle here. Right there is C cosine theta. And that's the altitude of this three-dimensional figure above the parallelogram down here in my XY plane. And that parallelogram might be a little hard to see, and I'm not sure if it'll make it a whole lot easier, but I think that's good. Here, 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 and here. Okay, so there are the four sides. They're shaded. Here's one side. Here's another face. Here's another face. The volume. Now, order of operation, do you do the cross before the top? But be sure I'll put that in the parentheses. Magnitude of this is the area of this base. C dotted with that multiplies the magnitude of C times cosine of theta. C cosine of theta is the altitude times the magnitude of A cross B, giving you area of the base times the altitude, which is how you should have learned to understand the volume of a three-dimensional figure. Now, the three-dimensional figure with parallel sides, three-dimensional. Not really parallel like that reason. Okay, I guess maybe it is. Anyhow, there we have it. Yeah, that's kind of neat, kind of good to know.